This figure represents the OpenAirInterface design and implementation of the 5G UPF. It consists of two distinct layers: the management layer and the data path layer. 1. Management layer. Enclosed within the user space. It operates as a core library implementing the 3GPP specifications. 2. Data path layer. Hosted within NIC driver. This layer is responsible for processing the user traffic. It is an eBPF service function chaining (SFC), responsible for parsing, filtering, classifying, and redirecting user traffic based on the rules received by the SMF, aka PDRs, FARs, MARs, and BARs. We are interested into subjecting our UPF solution to rigorous stress testing to measure its performance. Using RFC 2544-like tests. The system under test comprised a loopback between two devices. One hosting TREX and the other houses UPF. See figure below. The configuration of such interfaces is shown in the dashed boxes. The TREX machine hardware characteristics are shown here. This machine is using AMD Ryzen 7 with 18 cores processor and max frequency of 4672 MHz. And different caches ranging from 256 KB for L1 to 16 MB for L3. And a RAM of 16 GB. Regarding the network interfaces, TREX is using dual Mellanox Montana 28800 Ethernet controller with 100 gigabits per second speed. The UPF machine is using an AMD Ryzen 9 with 12 physical cores processor and 2 threads per core, which can reach up to 5732 MHz. The cache sizes range from 384 KB to 64 MB for L3, while the RAM is about 32 GB. Regarding the network interfaces, we used the same technology as TREX. In this implementation, a Python script is utilized to mimic the control plane functionality by initiating and managing PDU sessions. This Python-based method allows for a lightweight and flexible approach to testing and simulating different aspects of 5G network behavior without relying on a fully deployed control plane infrastructure. Let's now run the setup. After the UPF starts using the config YAML file to configure its reference points N3, N6, and N4. In addition to other aspects of the network, it also starts a UDP server listing on port 8805 for PFCP exchange, and attaches two entry points eBPF XDP programs on the N3 and N6 interfaces. The UPF now is started and listening on port 8805 for PFCP requests. Let's now establish the PDU session between a UE, in our case TREX, and UPF. For that we just need to run the Python script that we described before. The script sends a PFCP association, followed by a PFCP establishment. Then PFCP modification requests the UPF. After receiving these PFCP requests, handle each one and responds. The PDU session being created. Let's now check on the interfaces that no traffic was received before starting TREX. As we can see here, there is no traffic received on both N6 and N3 interfaces. Now let's generate the traffic from TREX. We first start the server, then start TREX console, and run a Python scripts to generate UDP traffic. The results shown here describes the very exciting performance of our UPF. As you can see, we are generating around 100 gigabits per second on port 1 and receiving more than 98 gigabits per second on port 0 in a loopback, crossing the UPF. The results also show zero packet loss, which means that the UPF is completely able to handle such amount of traffic. We believe that we can go farther and generate more traffic. Indeed, as we see here, the bottleneck is the hardware network controller, and the link utilization, which is a wrong 100%. Now, let's see on the UPF. Here XDP monitor is showing that we received traffic, and really few packets were dropped, order of hundreds of 10 millions per second. Regarding the CPU utilization, It is really low comparing to DPDK solutions and to the proportion of the traffic amount received. We talk here about 20% of CPU load in average.